Hello, Mr. Kerrigan. This is Minh and Geoff's physics lesson on moments of inertia. Earlier in the year, when we discussed linear motion, or one of the earliest concepts that we discussed was impulse and momentum for that system. So F equals ma was pretty much the foundation of our entire discussion of momentum and concept of Newton's second law. Now, if we were to try to develop a system that resembles momentum, but for circular motion instead of linear, we could derive a similar set of equations that would allow us to measure the change in velocity based off of forces for a system moving around a central fixed point. The main equation that we operated with was F equals ma. So if we start by looking at our equation for the linear motion, what we see is we have, in the three terms, we have a force term, a mass term, and a change in velocity term. A circular motion, we describe forces with torque, which equals the force being applied times the radius from the center, r. And if we rewrite this, we get alpha equals a over r. So now from here, what we want is an equation where we are able to determine a relationship between the torque and the alpha. So some coefficient for this alpha. And out of this coefficient, this little question mark box here, what we want is an ability to model the change in angular velocity based off of a torque applied for some given point particle that's moving in a circular path around a fixed point. So if we begin by looking back at our equations equating torque and the F equals ma equation, we can see that we get F equals torque divided by the radius, and A equals alpha times the radius. So now let's try substituting these two terms into the F equals ma equation. And we know we don't have to change m because mass is a immutable constant. So we can switch in for F, we can switch torque divided by r equals, on the other side, then we have m, the mass of the object, times alpha times r. So that is a substitution for the F equals ma equation with all the quantities that we want to use to describe our circular motion system. So we haven't changed anything, we've just rewritten it effectively and substituted these constants for the ones that are used in linear motion. And then if we combine the like terms of the r, we can simplify this equation to T, or torque, equals m r squared alpha. So this is the equation that we've been able to derive to model the change in velocity, the change in angular velocity of a point particle orbiting around a point and being acted on by a torque. Now, from here, so this is, you could consider an equal counterpart to the F equals ma equation that we began with just for a circular motion system. Now, imagine we have a more complicated set of individual mass particles orbiting together in a system. How might we go about assessing their net inertia? So for instance, what if we had a solid rod of uniform mass orbiting about a central pivot point? So now what we could do here in this situation, or what we might think to do, is think of taking an integral, which is to say, take an infinite amount of infinitesimally small sums and combine them together in a coherent way. So for this situation, what we need to do is adding together a set of particles, a set of infinitesimally small mass particles based off of their respective radii. So the next step in our process of assessing this moment of inertia will be writing this integral. So we know from our inertia equation of I equals mr squared that we need to multiply and sum an infinite number of infinitesimally small mass particles with their radius squared. So our integral needs to look like needs to have the radius squared times the dm particle, which is our miniature infinitesimally small particle of mass in this in the object we're evaluating. Now, as you'll notice, we're integrating here in this integral the radius with respect to the mass. So in this form, this integral can't be solved. To put this in a form that we can solve, we either need to substitute the dm with a dr component and maybe some component multiplied with that, or the r squared, we would need to substitute that for a term expressed by the variable of the mass. So for our purposes, it's more practical to substitute the dm for r, because that way we can integrate with our bounds being the center of the radius that's being traveled around, and the outside of it, the full length of the radius. For instance, if we were integrating for a rod rotating around one of its ends, we could integrate from the center of the radius to the full length L of that rod. To substitute that dm, we need to write an expression relating m and r, so that way we can solve for the m and for the dm and substitute that in. For this rod equation here, the mass at any given radius from the origin is the radius times this constant that's like an analog for density, sort of, but instead of being for volume, it's for length. So it's the total mass of the rod divided by the total length. So at any point r from the origin, the mass of that rod on that interval is the radius times this lambda constant. So what we need to substitute for is the dm, not an m, not a regular m. So if we differentiate both sides of this expression, the m equals r lambda, we get dm on the left equals lambda, because it's a constant that remains, times dr. And this equation is perfect because it allows us to substitute the dm in our integral for lambda dr. Since we are integrating this with respect to r, the bounds will be the origin, where we begin, which is 0, and the full length L of the rod that we're evaluating. So now we're ready to solve this integral, and it's a straightforward power rule. The integral of any function to a power n is, or the antiderivative is 1 over n times that variable to the power n plus 1. So here that's r to the power 3 times 1 over 3. And since the lambda is a constant, we can pull that out without having to modify it. And we evaluate this new function on the bounds of our integral, which is 0 to the length L. All right, so now we're doing well. I'm going to plug our original values for lambda back in to replace it, so we'll be able to cancel things out a little bit more easily when they appear. So solving this interval equation out, we get 1/3 ml squared cubed, times m over L minus 1/3 times 0 squared m, or cubed rather, m over L. And we are ready to combine like terms and cancel out. So we can cancel out the last term entirely because of that 0 squared. And we can reduce these two L components in the first term and rewrite it so we have 1/3 m L squared. And that is our total inertia. And if you look at our answer too and consider it, what you'll also notice is that we have the same units of inertia that our original equation has. So it's kilograms from this mass component and meters squared from our L squared component. All that's changed versus our point particle analysis is that we have a new coefficient in front. And it makes sense looking at it too that it's 1/3 because more of the mass is brought towards the origin, as opposed to a point particle of the same mass and radius would have all of its mass concentrating at the farthest r. So this has been analysis of a rod around its end.